Assalamualaikum warahmatullahi wabarakatuh. Good morning, class. We are the last group and we'll discuss about sales management. So there are four of us, Muhammad Raihan Laksmono, Rofi Noval, and Safa Sapir. So this is the content of our presentation. The first subtopic will be explained by me, Safa. The second will be explained by Raihan Laksmono. The third by Muhammad Raihan. And lastly by Rofi. So tailing dam. Tailing dams are an earthfill dam. It is used to store mining byproducts after the ore has been separated from the gangue. Depending on the topography of the site, the dam can be built across the river valleys or as curved or multi-sided dam walls on valley sides. This will facilitate drainage. So this is one of the construction method. This is the water retention type. So depending on the geological condition and process characteristic, impervious liner may be required for the tailings. It is made from clay or plastic to hold the seepage from the tailings. The next three construction methods are the conventional ones. So the first is the upstream. The new level of the raised dam are built on top of the previously deposited tailing. These tailing dams are the cheapest, but it is the most dangerous because the starting dike can liquefy and collapse, making the whole structure could be unstable. So this is the downstream, the second conventional method. The new level of raised dam are built outwards from the tailings and on top of the previous raises. Each new level, each of the dikes, are structurally independent of the tailings, and it is considered safer rather than the upstream tailing dam. Most storage water is possible with this dam. This is the only method that permits design and construction of tailing dams to be acceptable for engineering standards, but it is the most expensive because it needs greater fill volume. The third is the center line. So new levels of the raised dam are built on top of the tailings as well as the existing embankment. So the tailing placed on the downstream slope should be compacted to prevent shear failure. It requires smaller volume of sand fill to raise the peak, but it must be considered when raising the upstream phase because we need to make sure that there won't be any unstable slopes. This figure, the 16.8 figure, represents the water gain and loss at tailing dams. The water volume and water rate can be controlled to a large extent without precipitation and evaporation. It's challenging to quantify the amount of lost water, but it can be minimized by selecting a site with impervious condition or seal it with artificial layer made of clay. To minimize the seepage for upstream method, we can use barren starter dike, whereas for the downstream and for the central line, we can use free draining gravel blanket. So this is the treatment of tailings with lime. This is used to neutralize acids and precipitate the heavy metals as insoluble hydroxides. The treated tailings may be thickened, and the overflow, which are free from the heavy metals, will return to the mill, whereas the underflow will return to the tailing dam. The water reclamation system is the recycling of the water. This is important because lots of water must be reclaimed from the tailing ponds for reuse in the mill, and the volume of fresh makeup water used must be kept at minimum. The tailings from mill will go to the main dam, and it will move from the seepage pond to the tailings pond through the floating pond. So it will be here and here. And then the tailings in the tailings pond will go to a reservoir through another floating pond, and it will eventually go to the mill. And the makeup water also go to reservoir and eventually go back to the mill. The main advantage of this water reclamation system is the recirculation of pollutants to the mill, which can interfere with processes like flotation. This is all from me. The next subtopic is backfill, and it is going to be explained by Raihan Laksmana.
So, my name is Muhammad Raihan Laksmono, and I'm going to explain the backfill part. So, first of all, the introduction. Mine backfill is soil or overburden or imported aggregate material used to replace excavated zones created by the mining operation itself. So, the purpose of the backfill is to enhance the mine by allowing increase or recovery, stabilizing the ground, reduce the cycle time, and not negatively affect the underground performance. So this is the example picture of backfill. Then there is the types of backfill can be differentiated into three types. The first one is hydraulic fill. Hydraulic fill is any kind of backfill carried by water through the pipelines. The hydraulic fill is very simple. And then the second one is paste fill. Paste fill is bound with cement to create a very strong product. So there's the cement on the cement mixture on the paste fill. Later I will explain about that. And then the third one is rock fill. It is can be cemented or non cemented. It made of the waste rock placed underground by means of truck conveyor or races. So the first one is hydraulic fill. So these fills are made of the mill tailings itself, and then the fraction of fines is then removed through a process known as desliming, whereby the entire fill material is circulated through hydrocyclones. So the hydrocyclones are used in this hydraulic fill to desliming and watering. Desliming is like the because the fills is slimy, and desliming makes the fills not slime again, and the watering is reduce the amount of water in the mill in the fraction of fines itself. After desliming and watering, the fine fraction is the fine fraction is removed and then sent to the tailings dam. So here are the example. Uh, as we can see on the right picture, the remaining hydraulic fill fraction is reticulated in the form of slurry through pipelines to underground voids. So the condition is very slurry. And then for the left one, it's the hydraulic fields itself. And then as we can see, it's located in the high area because hydraulic field should be placed at the highest possible solids density to minimize the amount of excess transport water that must be drained and pumped to surface. And there is the watering process. And then we goes to the paste fill. Paste fill is prepared, retaining more fine particles and dewatered to a toothpaste-like consistency. It is also the densest form of backfill as a backfill material. So the resulting paste does not drain, So to eliminate the risk of subsequent liquefaction and remobilization, all paste fill must contain some binder. Binder is cement. So paste fill must be mixed with a cement. It is typically placed at 75% to 80% solids by weight via high pressure boreholes or pipelines. Here are the photos example. As we can see, it's very toothpaste consistency, and it's like the surface is like a cement. Uh, so paste fill can be placed underground at rates of 100 to 200 tons per hour. But for the same volume of fill per hour, paste will be introduced at a higher rate because there is less water in the paste fill. So the third one is rock fill. This type of fill is prepared using waste rock that is crushed or uncrushed, to which may be added cement or water slurry. If it's added with cement, it's called cemented rock fill. It is placed using trucks or loaders, sometimes via raised or large diameter boreholes, because it's enormous tons of rock, so it will be easy to place it using trucks or loaders. So generally the field has a poor size grading, a high void ratio, and is prone to segregation. So this picture shows a meta truck field. The left one is being placed by the truck. If you can see, there's the, I think, excavator or maybe bulldozer. It's moved the rocks to the hole. For the right one is, as you can see, there is a cemented rock fill. It's mixed with some binders or cement. Placement usually involves simply passing under gravity from a surface or in an underground. So here are the processing plan of the backfill tailing process. This one is, I think, a cemented tailing backfill, CTB, cemented tailing backfill, or paste backfill. So from the processing plant, from the mill tailings goes into the hydrocyclone process, and then goes under flow into the thickener, where when in the thickener the water is drained out, so it will be toothpaste consistency, as I explained earlier, and then goes into this filter for filtering the slurry, so there is no excess of rocks or mine or coals on the slurry paste, and then goes into the mix. The filtrate is goes to the back to tailing ponds, and then after filtering goes into the mixer, and then to and then go to underground as a form of paste or cemented paste. Uh, eh, and in the mixer process, it added binders or cement, and then goes to the underground. Here are the backfill plan location. The picture in the right is the example of the backfill plan. So there is two perspective for making the plan location. From the operational measurement perspective, the preferred location for backfill plan processing mill, it is usually adjacent to the mill. But from the technical perspective, it is better to it close to the locate it close to the top of the boreholes or pipelines that takes the fill underground. So there is why, because to eliminate the need for surface pumping. So here are the advantage and the disadvantages. The advantages is higher extraction rates, giving better resource recovery and longer mine life, improve ground stability, and a better security of ore reserve and infrastructures, and then reduce land requirements and disturbance for tailings disposal. Disadvantages is high costs, particularly if cement are used. So if we adding binders or cement, it makes this process is very high expensive. And then if we going to use the backfill, we have to require the positive displacement pumps for a high density tailings discharge, and it's not cheap, it's expensive. And then there is the risk of liquefaction of the tailings if saturation levels are high and can trigger a seismic vibration in the underground. So liquefaction is the spill of the liquid and can trigger the seismic vibration. Okay, that's all that I can explain to you guys. Thank you for listening to my explanation. The next one is densified disposal, in-pit disposal, and submarine disposal will be explained by my friend Muhammad Raihan. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Okay, now I'm going to explain about densified disposal, in-pit disposal, and submarine disposal. Densified disposal, thickened tailing or densified disposal, involves the mechanism of process of dewatering low solid concentrate slurry. This is normally achieved by using compression or high rate thickers or a combination of thickers and filter presses. When the deposit from the end of a pipe, high density thicket tailings or HDTT are then defined as tailings that have been significantly dewatered to the point where they will form a homogeneous non-segregated mass. The idea of a HDTT is to stack the pulp to form a self-supporting conical pile, thus reducing the height and retention force of the containing perimeter embankment. Okay, now this is the process and the equipment of the HDTT or densified disposal. And then here's I'll show you the video of the process. Okay, now we're gonna talk about the advantage of de-densified disposal of high density thick tailings, or HDTT. The advantage are no large starter dam is required, which significantly reduce capital costs. Reclamation costs are significantly lower than impoundment that store tailings and water. This is particularly true when considering a thickened tailing facility can be progressively restored, thus reducing closure costs. Uh, Concern of instability of high retaining embarkment associated with conventional storage are potentially addressed. The fourth one is little or no bounded water to manage, which not only reduce seepage, but reduce water pumping costs to and from the processing plant. Uh, and last one, little or no solid or liquid separation result in less oxygen in gas, which will reduce oxidation and thus the generation of acid from sulfur being tailings. Now is the in-pit disposal. Open pit mining creates void, and it would seem that the most environmentally responsible place to store tailings would be in the void that were the source of the waste. Although tailings disposal in complete open pit may sterilize resource and a single open pit might not be available for tailings disposal during active mining operation. In pit tailings disposal is the method of backfilling abandoned of open pit surface mines with tailings. This approach appeals to mine operator because it allows to filling of workout void at fraction of the cost of planning, building, and running a traditional thickened paste or dry stack facility. This is the pictures of in-pit disposal. And now the advantage and the disadvantage of the in-pit disposal. The advantage in pit storage is that the tailings do not require a retaining wall. Thus, the risks associated with embankment instability are eliminated. Disadvantage first, underground mines is close vicinity to a pit to an in-pit. Tailing visibility could be jeopardized. The increased weight of the overlying tailing can cause convergence in underground roadways, or liquefied tailing may rise into underground void, causing disastrous consequences. Poor consideration can result in long duration of surface deformation after a pit being filled. This is mainly due to the low solid content of tailings and depth of the stored material. The last one is as consequence where environmental law exists, the backfilling of pit is either forbidden or controlled to prevent excess groundwater contamination. And now we're going to talk about the submarine tailing disposal. Submarine tailing disposal, or STD, is the best solution for tailing disposal, where they say that storing tailing on the land in this land region is risky because the Western Pacific experience earthquake, and some land has many mountainous island that no place for on-land storage. And some land is area where land is originally needed for agriculture and has high rainfall in the land of making tailings dam vulnerable to collapse. The process is by pumping tailings into the sea and deposit tailings into deep water of the sea where there's little oxygen. We remove unsightly by doing it we can remove unsightly tailings on land. SDD is also relatively cheap mine waste solution. This is the pictures of the submarine tailing disposal. And here's I'm going to show you about the other pictures of the tailing disposal. Okay, now I'm going to talk about the in-pit disposal advantage and disadvantage. The advantage is a small terrestrial footprint, low running costs, RD not an issue, minimal post-closure treatment and maintenance required, and the disadvantage are burial and smoothing of the neck fauna, removability of tailing and release containment, water column, impact of secondary tailing plumes which peel off from the main density current. Impact on deep sea ocean are largely unknown. No possibility of tailing reuse. Restricted to mine located close to coast. Cost of remining environmental investigation and their duration. Potential contamination of marine food web, which may affect coastal communities. For the next topic, my friend Rofi will be explaining the topic.
So moving on to the next part, my name is Rofi Noval Maulana, and I'm going to describe about the reprocessing and reuse of tailing. And so the remining of tailing is the option we can use to recycle the tailings. There's the option to remine legacy tailings. This is the possible through using new techniques to recover more valuable minerals, as is currently being achieved in Australia's Northern Territory gold mines. Meanwhile, remining all tailings for metals that were previously ignored or discarded, like lithium, the 21st century golden child in the renewable energy boom, to fund our technologically driven world turns waste into a new treasure trove. And we can use the tailing as a resource. This is another productive means of utilizing tailings is to create more sustainable byproducts. This includes everything from commercial shotcrete and concrete products for self-sustaining uses such as mine roads, bricks, and tile manufacture, insulation, or even foam products. Tailing as a resource has further positive implications for the environment by recycling existing waste into manufactured products. Less tailings require storage, and as in the case of backfill, less water is trapped within the tailings. Another option we can use is the reuse of mine waste. Ideally, the reuse and recycling of mine waste, like other recycling efforts, create financial assets, slow consumption of natural resources, limits waste production, encourage innovation and local industries, create jobs, and teach responsibility for the environment shared by all. In addition, the reuse and recycling of solid mining waste and mine waters may also decrease the exposure of humans and ecological receptor to contaminated materials. Various reuse and recycling options have been proposed for mine waste by numerous researchers. Today, only some of these options, such as reprocessing and using tailings as backfill, are commonly applied at operating mine sites. And here are our references for these presentations. Thank you for listening and hope you have a great day.